Okay, so you've done W35. You've gone over notes pages 8 and 9. Let me repeat that. You've done W35. You've gone over notes pages 8 and 9. And now we're on to the real deal. Just set up the givens and solve it problems from page 10. You've done W35. That sets you up with the idea of where these givens come from. Okay, now let's get busy on this one. Example 8, you throw a ball upward with a velocity of 20 meters per second. Wonderful. And it returns to the ground. Good. Now, what do we know about this? We have been choosing down as positive because it made sense. The drop problem. The acceleration, down. The displacement, down. The velocity, other than the initial, the velocity throughout the problem, down. It made sense to call down positive. Now we have the throw down problem. The acceleration, once it leaves your hand, down. The displacement, down. The velocity the entire time, down. Made sense to call down positive. But now we have the throw up. And let's think about the throw up at first. We throw this thing up in the air. Which way is the velocity as it's moving up? Up. Which way is the displacement as it's moving up? Up. And which way is the acceleration as it's moving up? That's still down. That doesn't change. But now we have two ups. Velocity and displacement are up, but the acceleration is down. Well, as it turns out, for throw-up problems, it is easier to choose up as positive. You may say, oh, but I don't like, listen, you want to choose down as positive? Fine, but you better pay attention that your VI and your displacement at the peak or on the way up, they're all going to be then negative. So here, choose up as positive. That's what I recommend. I'll talk you through it, how we set this up. So how long does it take the ball to reach the peak? Because it's thrown upward, and I know I like up as positive. I'm going to come over here, put a little... This is not different than what we did before in the past too. I mean, heck, if it said east, you wouldn't be upset about east. Put it positive. Here it says up. Up is a direction. So, the ball is thrown upward. Good, up is positive. There it is. With an initial velocity of 20 meters per second. So let's put our givens with units over here. So VI, this is being thrown up. So then up is positive. The throw is up. The throw is positive. VI is 20 meters per second. Good. And it returns to the ground. Oh, we got lots of things to talk about. How long does it take the ball to reach its peak? Well, let's check this out. This is a projectile, so we know the acceleration is 9.81, but we have to be careful here. The acceleration is down. We called up positive, and now we're going to use a negative in here. How long does it take to reach the peak? How long is time? T, and what do you want? T to the peak. And this is a very important subscript. In fact, I'm going to use lots and lots of subscripts for these throw-up problems. I recommend you do as well. The time to the peak is what we're trying to find. Now, why do we need to know that it's the time to the peak? Because now we need another given. Notice we generally have 4. 3 we know, 1 we don't know. So we need another given. We're asking about the peak. Is there something else we know about the peak? Yes, the velocity at the peak. The velocity at the peak is 0. So we actually know that the velocity at the peak is 0, and we already have an initial velocity, so that will become our, we can put it over here, our final velocity at the peak is going to be 0. Now, are these the proper givens? Yes! These will actually get you what you need to get, because we have them correlating, corresponding. They're talking about the same thing. You want the velocity at the peak, the time at the peak. Good. Let's come over here. Let's do our equation. Now, looking at these, I know some of you like the delta V, but look, why mess with the directions? They actually give it to you. VI, AT, VF. There's an equation. VF equals VI plus AT. It's already all set up. You're solving for T, so some of you may like to do a little rearrange over here. Subtract VI from both sides, and then divide by A. T will be VF minus VI over A. It doesn't matter which way you do it, they all work. Okay, let's solve this thing, or actually let's substitute first. If we substitute, either way you want to do it, first one I'll do it both ways, but then as we move forward we won't. So VF here is 0 meters per second. You don't need the units over here if you put them over there. I'll do it, but you don't need to. Equals VI 20 meters per second plus A, be careful now, negative 9.81 meters per second squared times, where are we, T, and T is what we're looking for, so we'll call this T at the peak. Of course, you can do the same thing down here. This one is already set up for you to solve. I'll leave the units out this time. VF was 0 minus 20 over negative 9.81. Now, if you messed up your signs, in this case, you'll be sort of okay, but you'll get a negative answer. Time doesn't come out negative. So this will come out to 20 divided 10 roughly, or negative 20 over negative 10, gives you your 2 seconds. Listen, pause your video whenever you're ready, resume it. There it is. You get your answer. Okay. Next question. What is the total time the ball spends in the air? Well, the simple version of this is recognizing, and this does matter. Let me pause and say, there's a quick way to do this. You should be aware, because part of it is your understanding, and you are being tested. Do you understand that the way up matches the way down in time? You should. It also is an efficiency issue, because when I give you a quiz, do you recognize that the time up equals the time down? And so if the time up is 2 seconds, the time down is 2 seconds, the total time is simply 2 times the time up, which is just going to be 2 times 2 seconds, 4 seconds. Or do you go through and solve this thing with all the givens and everything else? That's part of where you have to realize, oh, wait a minute, I run out of time, I always get stripped. You got to know these little things. If you wanted to, you could solve this the full way. In fact, you could do this same exact set of givens, except you want the time at the end. The time at the end, the total time. And so your givens will be very similar. Which given will be different? Is the VI still 20? Yes. Is the acceleration still negative 9.81? Well, we're still calling up positive, so yes. Is the time at the peak what we still want? Well, no, we still want time, but now we want it at the end. And so, does another given change? Yes, the VF at the end. What's the VF at the end? Well, I would like you to know that at the VF at the end is just going to be negative the VI at the launch. So we come over here, and it's just going to be negative 20. And some of you may say, oh, wait. What about the displacement at the end? Actually, you could use that one too. You could even tack on, let's fit it down over here, you could even tack on D at the end is 0 meters. And now you have options. With these 4, I'm not going to actually go through and solve them, you could do that. But with these 4, 1, 2, 3, 4, you could do VF equals VI plus AT, and it works out just fine. In fact, you're going to have VF minus VI, which is negative 20 minus 20. That's negative 40 divided by negative 9.81. It's about negative 40 over negative 10. There's your 4 seconds. You could also do this with VI, let's see, A, which we're trying to find, T, and D. There it comes out a little bit uglier because, well, you'd have to do your quadratic, and you're not that big a fan of doing that, most likely. But you can, it'll work. All right, on to the next one. Calculate the maximum height the ball reaches. Well, it's a throw-up problem called up positive. I'm write my givens with units. What do I know? I know the VI is 20 meters per second. I know the acceleration is directed downward, so I'm going to call it a negative 9.81 meters per second squared. Max height, that's D at the peak. That's what I want to know. D at the peak. So what else do I know about the peak? Actually, I know a couple of things. I can use VF at the peak, knowing that that's 0. Heck, I could even use time to the peak because I figured that out earlier, and that came out to 2.0 seconds. So again, we actually have choices here. And so I'll briefly, leave it up to you to really solve these, but I'll briefly give you a couple options on equation. If you choose VI, A, D, and VF, you can use the equation VF squared equals VI squared plus 2AD. And if you want to rearrange that for D, subtract VI squared from both sides, and then divide both sides by 2A, and you'll solve for this. So VF squared is 0, so that's easy, minus VI squared, the VI is 20. It's 20 squared, which is 400, and there's a negative out in front. So we have a negative 400 over 2 times negative 9.81. Well, there's a negative about 20. It's 19.62. So negative 400 over negative 20, that's like 400 over 20. There's your 20 meters. If you instead want to use VI, let's see, A, D, and T, you could do it that way. So an alternate equation over here, this one is from the previous problem, an alternate equation here is D equals VIT plus 1/2 AT squared. And we already have this set up for D, but I'm going to warn you, 20 times 2 plus 1/2 negative 9.81 times 2 squared. Only the 2 is squared. If you don't put that negative in here, on some of these others, you're like, oh, I just got negative 2 seconds, I'll just make it positive. Well, or here, I just got negative 20 meters, I'll just make it positive. This equation, if you don't make sure your signs are right, you'll be adding instead of subtracting. That makes a significant difference. That actually gives you a totally different answer. So be very careful with this. Hold on 1 second. Making a video, what do you want? Oh, come on in.
I'll be quiet.
Okay, so let's go look at question 35. Question 35, let's set up our givens. All right, what is the ball's velocity as it reaches the ground? This is the same scenario as we talked about in question 33. I expect you, and so does the state, to have an understanding that the launch speed, gravity, slow, 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 stop, that same gravity, speed, 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 back to that starting speed. That's part of your understanding. So really, what you should recognize here is what goes up must come down. The velocity at the landing is going to be negative the velocity at the launch, as long as we're at the same heights. And most of the problems will be. So really, you should simply say VF at the end is negative VI. So VF at the end is negative 20 meters per second. Done. There's our answer. Alternately, you could still set up givens for all of this business, just like we did before, just like we did on question 33, looking back at 32. If you needed to, well, we still know that the VI is 20 meters per second. We still know the acceleration is downward, negative 9.81 meters per second squared. There's a decimal in there. They want to know the VF at the end. You should always put a little subscript on there telling you what you're looking for. The VF at the end, the reset. VF at the end, some amount of meters per second. And then you need another given here. So you have options again. Your two options, of course, you could use the time at the end, which we figured out earlier was about 4 seconds. Or you could even use the displacement at the end, which we know is 0 meters. And so we had the same sort of scenario as question 33. And you're welcome to run this. It'll work. I'll give you the two sample equations again. If you choose VI, A, VF, and T, it works out to that nice, easy VF equals VI plus AT. Makes sense, by the way. Good. So VF over here equals VI, that's 20, plus negative 9.81.